Today we're talking about projectile motion. This is the second part of ballistics, and we have two different types of projectiles that we're going to be referring to. We're going to have two situations. We're going to have a situation where we have an object being shot horizontally off of a cliff, and we call this like a cliff type problem. And then also we will have a object that is shot at an angle, and we usually refer to these as catapult type problems. I'm going to go to this simulation to talk about the horizontal projectile, my favorite website. This is a simulation of a projectile. Notice that when we get to the bottom here, this object has a x component and a y component of the velocity, but up at the very top, when t equals 0, t equals 0, think of t equals 0 as before I press the play button right here. This is t equals 0. There is no vertical component of the velocity if it is shot horizontally. That is something that you have to take into consideration when seeing the word shot horizontally. You have to automatically know that Vy is going to be equal to 0. Throughout this whole time, Vy will be changing. And Vy changes because it is accelerating because of the Earth's gravity. However, if we take a look at Vx throughout this whole time, Vx right now is listed as 20 meters per second. If I press play, go in slow motion after I press play, Vy changes. Vx does not change. The y position changes. The x position is changing, but Vx will not change because there is no sideways gravity. This whole time, it did not change. That's very important. That's sort of the crux behind the entirety of projectile motion. Vy changes. And in fact, it changes at a rate that you are very familiar with. Gravity still exists on this Earth. So the rate at which y changes the velocity, Vy is going to be 10 meters per second squared. When we were at the river problems, right, when we go back to the river simulation, what we found out is that if we have a river that doesn't have any motion to it, and we have this object go straight across, it's going to take that much time to go across. And then even if we added another component of velocity to the object, if we don't change this component of velocity, then we're still going to get the same time period. So what I'm trying to show you with that is this x and its y, when we are considering the components, they operate independently. Although the velocity over time will be increasing, it will be changing. As you can see, this v over here is going to be increasing because Vy is increasing. Vx is staying the same. Now, the total velocity of the object is greatest right at the moment before it hits the ground. That's what it will be referred to as, the moment before it hits the ground, or T final in this case. Not when it's actually on the ground, not when it's actually stopped and rolled and done all that. We're not concerned with that. We are talking about the very split second right before the object hits the ground. Now, the angle of velocity increases as the object approaches the ground. If we take a look, we have this angle theta that is describing the angle between the x-axis and the velocity. Or you could say that this is the angle which is going to be formed by the tangent or the inverse tangent of Vx and Vy. Because we start off with no Vy component, that means that there is no angle. However, as we go towards the ground, this angle, Vy, gets larger as we get towards the ground. And as you can see, if I put this in slow-mo again, the angle theta is going to be increasing as it comes towards the ground. Okay. Now, going off of that, the second before it hits the ground, we are still considering this part where it's fallen down at the bottom. We are considering that to be the point of 0. Now we are moving on to angled projectiles. What was easy about the horizontal projectile is that we shot it up at the top, meaning that we sort of shot it at its peak. This is the highest point it's going to be throughout the whole simulation. However, down here, we are going to be shooting it not at its peak, but at the bottom of its projectile. And we are left with the peak to be somewhere in the middle. Okay. So, what we're taking a look at is we know that if we were to have a vertically shot object, if we were to have a vertically shot object, we know that the velocity at its peak is going to be equal to 0. And as we can see, it's going slow, it's going slow, it's going, the object is going upward. And as it is going to reach its peak, at its peak, there is a velocity of 0. That is when we were shooting the object straight up and down. However, now we are dealing with an object that has an angle to it, is shot at an angle. 30 is what they used. And what we're going to see is if we go ahead and shoot it at this angle and we go into the slow motion, as the object approaches the peak right here, the y velocity at the peak is going to be 0. And notice that the entire time this is happening, this x velocity does not change. The x velocity does not change, and then the y velocity reaches its peak, or it reaches 0 when the object reaches its peak. Second rule. On the way up, Vy, just like we saw the other rule of if you reach the same height, you will have the same velocity. So let's take a look at, we're going to take a look. The peak is at 7.3. We're going to take this back a little bit. We're going to save that for later. If we launch this object, and let's use a height of, let's say when the object gets to 2 or 3 meters. At 3 meters, we're going to say that the velocity is 9.3 meters per second. The y velocity is 9.3 meters per second. The x velocity has not changed. We're going to keep it going, and it's going to go through its whole trajectory, and it's going to reach 3 meters again on the way down. Right now we're at 5, 4, 3, 2. Okay, come back. And again, we're at 3 meters per second. Now we're, instead of positive 9.4, we're at negative 9.4. We're at negative 9.4. The velocity is the same, except now it is pointing downwards. The y velocity is the same, it's just pointing downwards. So it's the opposite. Now, we're going to take a look at this launch angle and how it affects things. So if we have this over here, we can change the launch angle. And what I'm going to do is a very common launch angle to start at is 30. So if we take a look at the range of the object that I shoot, and our resistance is off, everything is all good. We go ahead and fire this off. We can see that it reaches a range of 28.6. 28.6. What I'm going to do is I'm going to go and increase it up to, I'll just increase it by 5. So I'll go 35, and it went further. I'm going to 40, and it went further. It'll go farther. It's going to now 45, and it's going to go its farthest. If I go back to, let's say I keep going to 50. Oh my goodness. Where 50? Right, now we're coming back down towards this way. And now if I go to 60, it reaches the same spot, 28.6, that my 30 degrees hit. 60 and 30 are complementary angles, and if I decrease the velocity, you can see that if we take any pair of complementary angles, let's take even 75 and 15. If we take 75 and see where the range is at, it's going to be 9.99. If I go down to 15, no way. Okay, we're going to have to change that. Let's make it 65 and 25. If I go 25 right here, hit right on the target because I'm money. We have 15.31. Let's go to 65, the complement of 25. We will hit the same range. However, we will notice that the time spent in the air was longer when it came to a higher angle. And the reason for that, yes. The higher launch angle will have a longer flight time because a higher angle means that you have a larger ratio of your VY compared to your VF. So if I change this angle over here, nice. If I change this angle right here, we can see that the larger the angle is, the higher Vy is, meaning that velocity in the Y direction is going to spend more time in there. It's going to take longer for the acceleration to bring the Y velocity to zero. And because it takes a longer time for the Y velocity to go to zero, then it's going to spend longer time in the air. Just like in the river problem, the only thing that affected the amount of time it took to get to the other side was the component that is parallel with this side to go the width of the river, this across this boat component. When we come to this problem over here, the only thing that determines how long the object is in the air is the y component of the velocity. The y is really where you find time in these problems. Okay. And then this is a little bonus. If you aim a projectile right at this monkey over here, if you fire it, no matter what is going to happen, eventually these two objects, because they have the same rate of descension, and because the velocities line up at the same on different heights, or they line up to be the same on opposite sides of the parabola, you end up going to have it where if you aim an object, no matter what the height of this monkey is, no matter what the velocity is, you are going to end up hitting the monkey on the target. So those are the rules that we need to know. You don't really need to know this last rule. That was a bonus, but these 5 are definitely very important for you to understand and internalize when it comes to these different types of problems. For angled projectiles, another thing that happens is it's when it reaches the same height. When we reach the same height, that is where the velocities are going to be the same. So if we take a look, for instance, if we start a little bit higher up and we have a little bit lower of a launch angle, what we can see is if we start over here at 9.1 meters, we can see that the Y velocity is going to be 12.9. If we get to the other side and we wait all that time, to get to 9.1 meters, to 9.1 meters, 9.1 meters, 9.1 meters, we're going to end up having negative 12.9 at the same time. But you do have the opportunity to go lower than that. So essentially what I'm trying to say is that the ground velocity is not going to be the same as the launch velocity. It's not quite going to be the same. But if you're at the same heights, the velocities will be the same, except they will be pointed in opposite directions. Gentlemen, that's all I have for you, and I will see you all next time.